G'day and welcome. In my previous video I explained how to find the equation of a line parallel to a given line, and in this video I'm going to explain how to find a perpendicular line in a very simple way. Now traditionally this is how it's done. We'd be given quite often an equation in gradient-intercept form or in general form. I might even make a general form. Let's say 3x minus y plus 5 is 0. And we'd be asked to find a line, for example, perpendicular to this through some point. And I'll make one up, let's say 2, 1. Now, I was just checking that it wasn't already lying on the line. The traditional way is to rearrange this so that we can get it into gradient-intercept form. Now, if I add y to both sides, I would get 3x plus 5 equals y. So the y simply appeared over here. Or, if I wish to write it in reverse, y equals 3x plus 5. Here's our gradient-intercept form, where 3 is the gradient and 5 is the intercept. Notice my pen's running out. And if we want a gradient perpendicular to that, we would say that the perpendicular gradient would be minus 1/3 or negative 1/3, what we call the negative reciprocal. So if this gradient, for example, is 3 over 1, the perpendicular gradient is 1 over 3 with the sign changed. Now, the reason for it, just so that you understand, is quite a simple one. Imagine that I have a line with a gradient of A over B. That's rise over run, A over B. So here's my gradient, A over B. And imagine that I wish to have a perpendicular line. So this is at right angles. If you pick this triangle up, I'll just shade it in. If you pick that shaded triangle up, move it over here and rotate it 90 degrees, it will fit in here. Now I think you can see that the side A will move into here, the side B will move up here. Shade it in, so that these are congruent, identical triangles. This angle here, at the other end of side A, I'll represent by a dot. So the other end here, represent by a dot at the other end of side A. And the angle here, at the other end of side B, from the right angle, I'll represent by a cross, and here's side B, cross. And you can see that the dot, the cross and the right angle add up to 180 degrees in that triangle. And the same dot, cross and right angle add up to 180 degrees in this triangle. Exactly the same size and same shape. If the dot and the cross and the right angle add up to 180 degrees, then I think you can see that the dot and the cross and this right angle also make 180 degrees, thereby confirming that we have a right angle. So these lines are indeed perpendicular. What is the gradient of this line? Well, it is rise over run, but I want you to notice something interesting. Here, if I, for example, started at this point and I was moving to this point up this line, I would go plus B, B in a positive direction along the x-axis, and plus A going up the y-axis to this point. So my gradient would be A over B, which is what we confirmed. Here, if I start at this point to move up to here, I would go backwards A units and up B units. So my gradient would be plus B over negative A. I'll represent the perpendicular gradient here. Plus B over negative A. Or, if I move from this point down to this one, travelling that way down the line, I would go down B against the y-axis, heading downwards, and then across to the right, which is plus a. And my gradient, rise over run, this time will be negative b over positive a. And both those have the same value. They're both b over a, and in both cases you've got a positive and negative sign which are worth a negative. So we can see that if we have perpendicular lines, the gradients can be represented by congruent triangles, and the gradients, if the gradient of the first one is a over b, the gradient of the perpendicular line is b over a with a negative sign. That confirms what we've done here. We flip the a over b to b over a, 3 over 1 to 1 over 3, and we change the sign, and that gradient is the gradient of a line perpendicular to our original. Now, forgive me if you already knew that, but I've got to assume that students watching this video may not. So I just wanted a little bit a revision on the side there. So we can say this, therefore the perpendicular line is y equals, using this perpendicular gradient now, negative 1/3 x plus something. Now, in my previous video I used a question mark for a little while. This line with that gradient is perpendicular to this line with that gradient. All that remains is to find this point. Now how do we find it? Well, we would have an infinite number of perpendicular lines, but we wanted to go through this point. And if it goes through this point, then this point must satisfy that equation. So we will substitute those coordinates into the equation and find this question mark. Now, we don't use a question mark in algebra. I suppose we could, but we prefer to use letters. Here in Australia we tend to use B. Some other countries might use a C or something. It doesn't really matter what letter. But once we find that letter, the value of that letter, we have found the equation of the perpendicular line. Let's finish by substituting x and y. The x value is 2, so I'll put it here. Now you know that 1/3 times 2 is 2/3, so I'll spare you that. Put in y equals 1. And you can see that adding 2/3 to both sides would leave b on this side. So b is 1 2/3 or 5 3. And we would say, therefore, the perpendicular line is y is minus 1/3 x plus b. Now b's worth this, so it's plus, I could write 1 2/3, I'll write 5 3, same value, and we'll talk about it. Now, this is the problem we run into in school exams, and it's also the problem I discussed in my previous video with parallel lines. If you're given the original equation in general form, you're normally expected to provide your answer in general form. So we would have to rearrange this. Now I'm not sure how close I'm getting to the bottom of the screen, so I will do it over here. We would multiply throughout by 3 to get rid of these fractions, so we get 3y equals 3 times that would just give me negative x or minus x, and 3 times this will give me plus 5. Just get these out of the way. Now, if we want it in general form, we want a positive coefficient for x, so we're going to bring that over this side where it will become plus x, and we'll bring the constant over as well, and we would get, normally I like to line the equal signs up, but it's not going to manage it very easily this time. X plus 3y minus 5 is 0. And that's the equation of our perpendicular line. This is the traditional way of solving it. You wouldn't do this, of course, that was just a little aside. But this is the traditional way. We would start with the equation we were given, rearrange it into the gradient-intercept form. Once we knew the gradient, we would find the perpendicular gradient by finding the negative reciprocal. And then using that, we would substitute the point we were given to find the missing constant. And that's what all this work was for. Once we found it, we would then have to change it back into the general form because that's what we were given. So, as I discussed in the previous video, this is an inefficient method. We start in general form, convert to gradient-intercept, solve the problem in the gradient-intercept form, and then have to convert back to general. Wouldn't it be nice to solve this without any conversions? Well, it can be in a very simple way. It just means that we don't know what the gradient is. That's really not a problem. We're not asked what the gradient is, we're just asked for a perpendicular line. So, as I did in the previous video, I'm going to remove the working and leave the original equation and the result and talk about the shortcut. So let's have a look at that. Now, when we rearranged it, just remembering this, to the gradient-intercept form, just by moving the y to one side, we can see the gradient was 3 over 1. And the question was, where did that come from here? Now, you can see that the 5 here had nothing to do with the gradient, it's still over here. The gradient, in fact, has a lot to do with this 3, and had I had, it's a little bit silly of me for not having one, but had I had a constant in front of the y, I would have had to divide by it. This was 3x minus 1y, and that 3 and that 1 produced the gradient. Therefore, if I wanted the identical gradient, that is a parallel line, I would leave this untouched. And my answer would have 3x minus y in it. If I wanted the negative reciprocal, then the 3 and the 1 change places and I change the sign. And if this gives me the gradient over here, then if I swap the coefficients and change the sign, it will perform the same function. That means that I can immediately say that the perpendicular line is 1x, wouldn't normally write the 1 of course, plus, changing the sign, 3y. Note, the 1 and the 3 have changed places, and I've changed the sign. I normally change the sign in front of the y rather than the x. And this line is perpendicular to that one, because that's where the gradient comes from. And I've now got a gradient with the two values swapped, and with the sign changed. And all that remains is for me to find the missing constant. And that's easy enough to do. I think I have the 0.21. So let's substitute and we'll find the constant. Now, x is worth 2 and y is worth 1. I'll just write x and y above here. So if I put 2 plus 3 lots of 1 plus k is 0, then here I have 2 plus, I'll write every step, 3 ones are 3, plus k is 0, 2 plus 3 is 5, plus k is 0, and k, subtracting 5 from both sides, is negative 5. Therefore, since I now know the k value, I put it back here, and I get x plus 3y minus 5 is 0, And that is my perpendicular line. And guess what? There it is, found the traditional way. But this way took that much work. I hope you appreciate the simplicity of it. We have not had to convert to the gradient-intercept form and then have to convert back. We've saved ourselves both those conversions. All we've observed is that because this part of the equation contains the information about the gradient, all we've had to do is reverse those two numbers in order to get the reciprocal gradient and change the sign. That has given us a perpendicular gradient. And the rest is just finding the constant. So I'm going to do one more, just so you can see it demonstrated. I might change the form of the equation, that might be a good idea, so you can see it in a different way. And then we'll finish the video. So let's have a quick look at another example. Well, let's think up an example in standard form. Now, standard form has the x and y terms on one side and the constant on another. So let's make something more complicated. Let's make it 5x plus 11y equals 6. So let's imagine we had that and choose some point. I'll use something negative this time. Let's do -2, 5. So I want a line perpendicular to this equation, to this line, passing through this point. So here it is with this faster method. I look at this and I think that contains the information about the gradient. I would have to rearrange the equation to find what the gradient was. So if the teacher asked me or the exam question asked me, I would have to do that. But if I'm not asked to do it, if I'm just asked for a perpendicular line, I say the perpendicular line is, leave my x and y in position, but to change the gradient to the reciprocal, I swap the 11 and the 5, and I change the sign. And now that line, I'll put a constant here, that line is perpendicular to this one, because here is the information about the gradient, and I've just created a negative reciprocal. How simple is that? I now get the point -2, 5, and I substitute. Another advantage of this, if it's in general form or standard form, is the x is first and the x is first here. So let's put the -2 in, minus 5 lots of 5 is k. That's -22 minus 25 is k. Putting those together, that's 47. And now that I know that's the value of k, I can say therefore the perpendicular line is 11x minus 5y equals, and k I now have worked out is -47 if this line has to pass through that point. And that's it, finished. That's a perpendicular line, or the equation for the perpendicular line to this one. So it's a very swift process, provided you don't have to do that double conversion. Oh look, I could go on and on, but I think that's part of my problem with these videos, I think. But I think that's enough. If you've enjoyed it, please like the video. I really appreciate your comment underneath. And if you're not already a subscriber and you'd like to see more of this material, then please subscribe so that as I post them up, you'll be informed. And as always, I thank you very much for watching.